It's Team 1025 and we're doing problem A, it's raining space dust.
Assumptions. To help simplify our mathematical model, these are our assumptions about the particle. We're assuming that the particle is mildly porous sphere, and as it changes in size, it keeps its spherical shape. We're assuming it has a constant particle density, and it hits the atmosphere orthogonal to the tangent line along the point of the atmosphere. We're also assuming that the particle is made of silica, as most cosmic dust is at around 50% silica, giving it a good average estimate on how it will react as it falls through the atmosphere. We're also assuming that it does not spin or rotate. The general assumptions we have made about the model are that we will ignore energy loss to radiation or light emissions. 50% of the kinetic energy is converted towards ablation. We are using an exponential atmospheric model. We are assuming that the drag coefficient remains constant, and we are only considering single-body ablation with no fragmentation. We are also going to ignore radiative cooling and assume that gravity is constant. And finally, we're going to ignore the Earth's spin, since it is negligible and will not harm the accuracy as the particle is so small. The creation of our equations. For the creation of the first equation, we're using the area of a circle, mass of a spherical object, the atmospheric density, and atmospheric friction to make our final equation for decreasing velocity due to drag. For the creation of our second equation, we use the velocity-enhanced ablation factor, the heat transfer coefficient, the atmospheric density, the atmospheric friction, the area of a circle, ablation, and finally normalized velocity to create our equation for the mass loss due to ablation. We made it a piecewise function, which is 0, to stop the particle from ablating when the velocity is less than the speed of sound. For the creation of our third equation, we use the mass of a sphere and the loss of mass due to ablation equation to create our final equation for the decreasing radius due to ablation. Using the same piecewise function, when 0, the particle size stops decreasing due to ablation.
Chosen constants and coefficients. 9.81 for gravity. Our drag coefficient was 0.25. Our particle density, we used 2650, which is the density of silica. Our air density was 1.225, which is the air density at sea level. The height scale of the atmosphere is 8e⁻⁴, and our initial height was 12e⁴, which is just above the Kármán line. Simulations. Dust comes in a variety of sizes and entrance velocities. We decided to use our model to graph the outcome of particles with a starting diameter in the range of 0.1 to 100 micrometers and an initial velocity of 10 to 70 kilometers per second. We utilized heat maps to help visualize different characteristics from the model. In these two graphs, the particle's final height is shown along with a binary red or green depending on if the particle reaches a height of 0, e.g. the Earth's surface. As can be seen, particles with smaller initial velocities last longer before disappearing due to ablation, or can even make it to the ground. Similarly, particles with larger initial radii also last longer. A combination of a big radius along with a small entrance velocity gives the particles the best chance of reaching the Earth's surface. Heat maps show the loss of mass due to ablation on the left, which, as you can see, is most of it for most of the particles that are traveling anywhere above about 12 kilometers per second. And the one on the right shows the final radius of the particles, either when they hit the ground or fully disappear. Since our initial heat maps, which ranged from 10 to 70 kilometers per second, only showed such a small slither of particles that were reaching the ground, we decided to zoom in and do some heat maps of just between 10 and 20 kilometers per second. When doing so, we found the boundary is around just below 12 kilometers per second. At this point, particles traveling slower reach the ground, and particles that are traveling faster upon entry only reach about 60 to 100 kilometers from the Earth's surface before ablating. From these heat maps, we can see that the greatest final radius occurs at just the lowest initial velocity and the highest initial radius. From there, any increase in velocity or decrease in radius results in a decrease in final radius, up until it hits the boundary, at which point the particle fully ablates. We found for an average-sized space dust particle to reach Earth's surface, it needs to enter Earth's atmosphere traveling less than 11.9 kilometers per second on average, or else it will end up vaporizing through ablation. Larger particles can survive higher speeds, most likely due to their increase in mass, which is used as a barrier to slow down the particle till it is no longer ablating. Smaller particles burn up easily if going too fast because of their less mass, or likely due to the limitation of not having a minimum energy required for ablation to occur due to our model. Higher initial velocities resulted in increased time to reach Earth's surface. This is most likely due to the higher velocity generating more energy, which ablates a particle, reducing its mass, which in turn reduces the terminal velocity of the particle. From our model, it would be partly possible to work backwards from the amount of cosmic dust found in a layer of Earth's surface to estimate what originally entered the atmosphere at that time. Since our model shows that the final size and mass of each particle depends heavily on its starting conditions, things like initial velocity and radius, as well as the height it enters from, we could work backwards to make reasonable assumptions about what the original distribution might have looked like.
Future thoughts and improvements. Future thoughts and improvements. We would like to add varying entry angles, as this would improve the accuracy to determine the entry from which the particles entered from the atmosphere, including a changing ablation depending on material, which will better model how our real particles behave. Currently, our model assumes a constant rate of mass loss, which can over or underestimate how much mass and radius is lost during ablation. A changing of particle density, the model could better predict how quickly the mass and radius changes over time. With our model, we assume that the particle stays uniform all the way through, which isn't always true in reality. Including the minimum energy required for ablation to occur per particle type, and adding change in gravity, which the change is rather small, but it would increase the accuracy of the model. We would like to also look into how volatile elements affect the particle, which could change how quickly cosmic dust may vaporize. And we would like to also include energy lost to light and radiation and shockwave, as this would improve the accuracy of our model, as assuming not all energy is converted to ablation. And finally, adding a change in drag coefficient depending on altitude would change how much energy is converted from the environment. These are the references we used in the research and making of this mathematical model.